Hi, everyone. How are you doing? Good? Yay! Thank you for coming to the last session of the day. I will say this, a little bit of a disclaimer. You will go away with a headache, I promise. There's a lot of fun stuff to talk about when it comes to asynchronous programming. But before we get to that, I think this has been an amazing conference so far. So would you mind giving a round of applause to the organizers? Thanks. This is going to confuse everyone else. Think that I finished very early because I want to run to the hotel to get some drinks. That's not the case. We're going to talk about asynchronous programming for the next hour. My name is Filip Ekberg. You can send me an email afterwards. For years, I asked people to send me questions. I thought that I was just super clear when it comes to building .NET applications and asynchronous programming. Never got any emails. Turns out, I forgot to put it on the slide. Well, that happens. Now it's there. Send me all your questions in regards to .NET or C# or asynchronous programming. All right, so why do we want to bother using asynchronous principles and going back to the basics and learning about how to be efficient when it comes to building applications and leveraging these principles of asynchronous and parallel programming? Because we'd like to avoid unreliable applications, and I'm not necessarily talking about .NET MAUI or Android applications. I'm talking about UI applications that freeze up or applications that are not performing as well as they should be. In terms of being unreliable, that is, we're maybe not handling requests properly. We're not offloading requests from the UI to background threads. And then when we get back from that, we'd like to handle that properly as well. So how about we'd like to improve the user experience here. What we want to do is to ensure that all our users get the best experience possible. And we can do that by applying some quite on the surface, simple processes and principles, but under the hoods, there's a lot of complexity that goes into the tasks and async and await. And that's what we're going to be focusing here today. So we'd like to efficiently consume APIs, that being APIs that we build ourselves. It could be web APIs. It could be talking to a database or using disk operations. All the APIs available in .NET, most of them support asynchronous principles and processes. So if we use that effectively and efficiently, our applications should become better. This really all boils down to one thing, and that's being able to leverage all the available resources that I have on my machine. Now, while this is my workstation at home, my phone is almost as powerful as a really powerful laptop or PC. It has a lot of CPU power. It has a lot of different cores. I can distribute work and do that effectively in the background. I have a really fast SSD, and I'd like to be able to communicate with the disk properly and do that effectively and efficiently as well. So using one API in .NET allows us to do all of this, handle distributing work across different cores and threads, as well as communicating with disk and I/O operations as well. So we can break this down into two things, CPU and I/O. And really, it's about asynchronous and parallel programming. They're fundamentally different and something that people very often confuse with each other. Asynchronous programming is about allowing us to take some work and offload that to a separate thread without blocking our current caller. That's often the UI thread, so I don't want to block the UI until that response is available. Now, when the response is available, I want to be notified, and that's what the asynchronous principles are all about. Offloading work and then get notified when that's available for me to process. While parallel programming is about taking a really big problem, distribute that across all the available resources, and solve it as quickly as possible. So they're a little bit different, but they can also be used together. And you'll see why in just a second, because .NET provides the same API to do both of these different things. So it's really about taking blocking code and producing non-blocking operations. So if we take for an example, we can avoid heavy lifting on the UI thread. I don't want to do a lot of work on the main thread of the application because that then can't handle input from the user, and the OS will eventually tell us the application is no longer responding. That's not very good. And I do want to say as well, it's not something that you should take lightly, but don't block any asynchronous operations. So once you start introducing asynchronous principles or use asynchronous APIs, don't force them to be synchronous. Don't force them to block by using .result or using the wait method. And I'll show you why later on, because this can cause deadlocks and some other problems as well. So really, if you go back to this non-responding application, there's a lot of work happening on the UI thread. The OS is telling us that this application is not responding. Do you want to kill it? Most users just kill the application and restart. I'd like to end up in a situation like this instead. provide a little bit of a better user experience, show a loading indicator, do the work in the background. I mean, if we show a loading indicator for a long time as well, the user will eventually kill the application anyways. But at least the user experience is slightly better. We can still build bad applications with good APIs. But to solve this and to get to a state like this here, where the OS don't think that the application has crashed, we can use the task parallel library. This allows us to do a couple of really important things. It mainly allows us to simplify the work for concurrent and asynchronous code. So both introducing parallel principles as well as doing asynchronous programming. So we can distribute work to another thread. When doing this, what it will actually do, it will take all the stuff that we have inside this lambda or anonymous method or the method we point to, it will schedule that to work on an available thread on the thread pool, if there's one available, that is. Now, this can lead to a couple of different problems. What happens if we do this a lot of times? If you're working in ASP.NET, for example, if you do task.run for each request, eventually you'll starve the thread pool and your application will not be as performant as it could be. So while this allows us to distribute work, we should be quite careful using this as well. All right, so it tries to reuse as much as possible internally as well to be as performant as possible. When we do task.run, not only does it consume an available thread on the thread pool to run that work, but it also reuses threads internally. So it will try to be as effective and as performant as possible. So there's quite a few things that happens when we do this. First of all, the work is distributed to a different thread. It doesn't necessarily always mean there's a new thread that's being created. It can be reusing an existing thread if that's not occupied by other work. So this can lead to data that's thread static that's being reused in that thread as well. So because a thread or the lower level threading can reuse data and have static data on it, if you have a task, that may leak data to other threads as well. So you should be careful when using thread static data. Now, what this does, when you call task.run, this actually returns an instance of a task, which allows us to then subscribe to when that work is done. This is known as introducing a continuation. So we can say, after this task is completed, I'd like to continue with some work. There's new ways to do this. We can use the await keyword, but we're going to get to that in just a moment. The reason we go back and talk about the really basics of what happens internally and how to build this is because this is really important to understand. So to schedule some work, we can do this in two different ways. We can create the just points to a method or run some arbitrary code that we'd like to schedule on the thread pool. Or we can say, I have a task that's going to produce a string. So I know that once this work is done, there's a result available of the type string. So how about we jump over to Visual Studio and take a look at an application that's not performing as well as it should be. I'm going to just make sure that I run the right application. Doesn't matter that this is a WPF application, could have been a WinForms application, a MAUI application, could have also been a ASP.NET Core application, but illustrating when threads block or when they're slow is much easier to do in WPF than in ASP.NET Core. So now when I click this button here, the UI freezes, I can't move it at all, and then after a while, it populates the UI with some information. So the problem here is probably that it does a lot of work on the main thread. If I go into the application, there's a click event handler. Let me just increase the font size a little bit here. This here calls a method called doSomething. If I go into that, we can very quickly see that this sleeps for 2 seconds. Now, I know some developers like to add thread sleep because it handles race conditions, and just sometimes it works better when it sleeps for a few milliseconds. Don't do that. And don't sleep for 2 seconds if you ever try to solve a race condition. So obviously, this is doing a lot of work. This is just to simulate that it's doing a heavy work or doing a process here. Maybe it's using an older API that loads something from a disk or a database. Not really the best. So how do we make this better? Now, without changing too much of the application, there's a couple of things that we could do. We could say that I'd like to schedule this work to happen somewhere else. But if I just simply take the whole method and say, I'd like to schedule this method to run on the thread pool, and I rerun the application, while the application performs a lot better, it doesn't do anything. It no longer populates my UI with any information. If I do the same thing and run this with a debugger attached, and click Run again, it's going to tell me that you're trying to invoke the UI from a thread that doesn't own that, which is problematic. So what happened here is that we're not allowed to update the UI because we're no longer on the UI thread, which is really a big problem, right? Now, why didn't I get notified with this when I ran the application without the debugger attached? Because when I do task.run, what actually happens here is that this returns a task, and this task that I get here actually contains an exception. So all tasks will swallow exceptions, and you have to monitor that yourself. You have to introduce code to ensure that this was executed properly. So we quite quickly noticed that this doesn't work. So we're going to go back and we're going to fix our code up a little bit to say, I'd like to call this method and instead go ahead and refactor only the portions that are actually slow. And to do that, I'm going to move this piece of the code into a new task instead. So I can say, I'd like to create this work. Let's move all that heavy lift into a separate thread. Now, if I run this again, this is going to behave a little bit differently from before. We're going to click Run, and just all of a sudden, we get all the data available in the application. So the experience is a little bit different from earlier, but slightly better. However, what if this data that we get here was not available until those 2 seconds were up? There's a lot of stuff happening here. What's actually going on is that we're going into this method, we're updating the UI, we're scheduling some work to run in the background, and then immediately running the next line of the code. But what if I'd like to wait for this to be executed only until this work has completed executing? This is where we have to introduce that continuation. So while I moved that work to a different thread, now I'd like to wait for that to complete before I continue executing the rest of my code. So to do that, I have to capture the task or append a continuation to it. I'm going to say task, because I'm really bad at naming things. And I can say, how about when you're done, I'm going to continue with some code. I'm going to pass some code in here, and I can get the completed task. And we're going to say, hey, I'd like to only run this code once those 2 seconds have completed. So now what happens when I run the application? Do you think this is going to work? Everything's going to be amazing? No, you don't trust my code? Let's see what happens here. It doesn't like that I have the application running, so let's try that again. I'm going to click Run here, and it's going to say, hello, Azure Dev Summit. I can move around the window, and it doesn't do anything else. So what's interesting here is that it does run the method. It's going to run for 2 seconds, and after 2 seconds, it's going to try and update the UI. However, when it comes to the continuation after a task is completed, all this code will also be scheduled to execute on an available thread on the thread pool, or execute in line with on the same thread that this was executing on. So that's a little bit problematic, because now I'm trying to update the UI again from a thread that doesn't own that object. In different types of applications, there are different ways to solve this. In WPF, we have something called a dispatcher. So we can say, I'd like to send some work off to the UI thread. And all of a sudden, the code starts to look quite ugly, and it's problematic. But now we're at a state where this is actually going to work the way I'd like to. I can move around the window. After 2 seconds, it's going to pop up here and update my UI. There are a couple of problems here, and this could lead to, for example, what happens if the UI is blocked here, or the UI is actually waiting for this to complete? We could run into a deadlock. I don't particularly like all these cross-thread communication. So while I was able to do this, it's not the best-looking code. I do want to go back to one thing, though. Even though we were able to offload our UI from that heavy work, the UI is no longer blocked, and we were able to come back to the work and execute that and update the UI properly. We weren't notified when there was an exception, right? Because the continuation is wrapped in its own task. So let me just show you exactly what I mean here. Let's say that we do throw new exception instead of updating the UI incorrectly again. This won't tear down the application. This won't do anything, because we will actually have a task that's returned from a continuation as well. So how do we know, and just to make this super obvious, task.run returns a task, task.continueWith returns a task. We'd have to monitor if this, I don't like that it's suggesting me to call wait because that would deadlock. So we'd have to do continue with the completed task. But then, what happens if this throws a new exception? We'd have to continue from this as well. Now, this is starting to look a little bit ugly, because if this fails, we'd have to continue with this as well. You get the problem, right? We can actually configure this so that it does throw back the exception, like the await keyword does. But this is what you'd end up with in the previous versions or earlier when you're applying this. And it's really important to understand that if you have a task and you haven't configured how to handle the exceptions properly, they'll all just swallow the exceptions. And you'll have to monitor if there's an is faulted state on it, and then grab the exceptions that are available on that task. Now, this code looks a little bit ugly, but we're going to fix that soon. But it's important to understand that once you append a continuation, if there's an exception and you're not awaiting that or not appending your own continuation again, that will also be swallowed. Now, someone is probably thinking, if you've worked with this before, there's a way for you to track unobserved exceptions on the task scheduler. Now, there's this thing, I think it's called, let's see here, just to illustrate a point, task scheduler dot unobserved exceptions. If you track that or add an event handler for this, this will be triggered when the garbage collector collects the task. But if the task blocks or locks or has something that's run forever, and the garbage collector cannot collect that, then you'll never get that exception anyways. So don't blindly trust that this method or this event is going to be erased. Anyone got a headache yet? No? Perfect. All right, so that's kind of the state of using the task. It looks simple, but there's a lot of things to keep in mind. Keep in mind that it does swallow the exceptions. So some considerations to take away from this here. Be careful when wrapping code in a task.run, because what happens is that maybe that performs a UI invocation, and then all of a sudden, while the application seems like it's working, there might be exceptions that are swallowed. In this very simple example, like we very quickly saw that this was a problem, but if you refactor a really large code base, that will quite quickly become a problem. And a way to get around this is to try to find alternative APIs that don't rely on you doing task.run. For example, if you're using the file class to read something from disk, like file.readAllLines, there's a read all lines async. Use that instead. Rely on the operating system and the internal versions of asynchronous APIs. I also want to say this, that thread static is unreliable. There's this thing called async local. So if you really have to have static data for an entire task, use async local instead. And we should always validate our tasks. As we see here, they swallow exceptions, right? So we need a way for us to validate that the task completed properly. And the way to do that is by introducing a continuation, either by using continue with or the await keyword, which we're going to get to in just a moment. And I said earlier that parallel and asynchronous principles are slightly different, but we can combine these two principles slightly. There's this thing called parallel extensions, or the parallel class. And the reason I've wrapped this in a task.run is because parallel.for is in fact a blocking operation. So what this will do is that once you call parallel.for, it will distribute that work across all your available cores on your machine and block the current one. So what I do here is that I say, hey, relieve the UI, don't run this on the UI, block a new thread, and then distribute the work across the rest of the machine. Obviously, don't do this in ASP.NET Core. If one request blocks your entire machine, it's not the best. And if you run in Azure, then you'll very quickly end up having an expensive bill. So avoid that. So we're going to make this a little bit better. So far, we've used the task and wrapped some code in that and made it a little bit uglier to read, but the experience is better. Now we're going to add these two contextual keywords. Now, async and await has been around for a long time, And they're simply contextual keywords. And that's important, because they only change the context of where they're used. They will introduce compiled code, because there's no concept in .NET of a state machine or of the async keyword or the await keyword. So the .NET runtime has no clue whatsoever about what to do when it sees these keywords. They're working on making that true, though. So in a future version of .NET, async and await will potentially be completely rewritten of how that works internally. They're calling it async 2. The keyword will probably be the same, but the implementation is called it. Naming things is hard. So what if the runtime would actually know about the context switching and of how all of this should work internally? That would be a lot better. Because when introducing these keywords, there's quite a few things happening internally. The whole idea is that we hide all the complexity of the code that I just showed you here with the task.run. So this should increase the readability of the code, but that also makes it more error-prone. Like every time we use a pattern to make something more readable and understandable, there's always going to be a side effect. And in this case, it is that if we don't understand how this works, it's going to make our lives a lot harder. Let's look at a simple example. This is how we use the async and await keyword. You mark a method as async. The async keyword is always followed by a task, because if it isn't, you're going to end up having some real big issues. We're going to get back to that in a moment when I show you why async void is not a good idea. Methods without the await keyword shouldn't be marked as async. These should always be used together. So really, there's 3 things that should happen. So always return a task when you mark something as async. Always await something. Now, notice how there's no task.continueWith here. What happens is all the code after that await keyword is actually moved into one of those continuations. So it's doing all the heavy lifting for us. It's also going to validate that there were no exceptions. It's going to ensure that we can capture that if there actually are any exceptions. So there's a few things happening when we introduce await. It marks where we want a continuation. Instead of us having to do .continueWith, this is doing that for us. It will validate that it succeeded or failed. If there's an exception, that exception will be rethrown. What also happens, which sounds a little bit difficult to comprehend, is that it returns to the caller with a reference to the ongoing work. So if you call an asynchronous method and that has an await in it, it will return back to you when it reaches that await keyword. We're going to look at that in just a moment as well. So what about then validating a task? How do we do that with the async and await keyword or the task continue with? Well, we can use await, which is very simple. Should always do that. Or we can append a continue with to ensure that it actually completed successfully. All right, so let's jump over to Visual Studio again. And we're going to try and make this a little bit better. Now, I mentioned earlier that instead of me rewriting this code and wrapping things in a task.run, it would be a lot better if I relied on APIs that were built for this from the start. Now, because this was just demo code that was just simulating some work, there's actually an asynchronous equivalent, task.delay. So I don't have to do task.sleep, for example. And the same goes for other APIs as well internally. Reading files from a disk, talking to a web API. If you're upgrading to a new HTTP client, there's only asynchronous operations available. So that's where you want to use this instead. And of course, if I'd now like to make this a little bit prettier, ideally what I want to do is to say, I'm going to take the debug text, and I'm going to update that with this result. So I'm going to get rid of all of this. But what I'd like to say is that, hey, I'd like to only run this portion of the code here at the bottom after this has completed. And the way that we do this is by saying, I'd like to create a continuation. Notice how it just automatically updated here. Changed it to async task instead of being void. I now have the await keyword. Just going to make sure this is not running. There we go. So now what I've done is to say, I'm going to run some asynchronous operation. That could have been a task.run, could have been an API call. I'm going to create a continuation. This code will only be executed after that asynchronous operation has completed. So let's run this for a little bit longer. Let's say 8 seconds so we can see what actually happens. I'm going to put a few breakpoints. And up here in this method, we're going to get some squigglies here as well, because I should really await this. What happens if I throw an exception in this method here now? Actually, let me just show you what happens. I'm going to run this without the debugger attached. Oh, come on. There we go. I'm going to run this, and nothing happens. This is because I've determined that this method is returning a task. And I'm using the async keyword, meaning that this here will be put on that task. Unless I'm validating that this happens, then I have no idea that there was actually an exception. So var do something task. If we go back to what we had earlier, we'd have to do continue with and check if there's an exception, right? Or we have to await this task. Do something task. There we go. And while this intelligent thing that just refactored my code here, it actually introduced a mistake here, because this is an event handler that cannot return async task. So now, let's get rid of that, because I don't want to tear down the application. Now what happens is that I have an asynchronous method that returns a task. If I await that, this will validate any potential exceptions and that the operation was handled properly. There's a lot more that's going on here. We're going to go through that in just a moment. Before that, I'm going to show you something. I'd like to do a couple of things. For example, I'm going to update my UI. With some text. I'm going to put a few breakpoints in here. I'm going to run this with the debugger attached. I'm going to click Run. I'm going to get rid of all of this. We're going to run into this method. And now what's going to happen is it's going to start off this work that's going to go on for 8 seconds. This will just immediately be scheduled to work on the thread pool. It's going to see the await keyword. And then what happens is that it's going to exit this method. It's going to run the code after that method call, so it goes back to where it came from and runs the next line of the code, updates the UI, finds an await, returns, and then after 8 seconds, we're back here to handle a potential result. We update the UI, and now, hopefully, this says, hello, Azure Dev Summit, came back from Async and then from Filip, right? So this is where it becomes a little bit tricky sometimes to understand where things are coming from and where things are happening. And notice I don't have any dispatchers. I don't have any cross-UI communication whatsoever. It's because all of that is handled by async and await. So just to show you exactly what happens, here we're on the UI thread. We go into the method do something. We're still on the UI thread. This work is not the UI. And then when we come back after this await, it will ensure that we're on the UI thread again. So this is all the magic that happens internally. It captures what's known as the synchronization context, so it captures that original thread. When we find the await keyword, what it does is that it takes the thread that this line is currently executing on, stores that, and then ensures that it runs itself on that same thread when the work is done. So internally, it's very clever. Now, I also mentioned earlier, like this is supposed to make it look easier on the eyes. We can now more easily work with this code, and it's supposed to be more readable. But I want to re-add one thing. I'd like to throw new exception, because this is important. Actually, let's move this to after when we're back. So I'm going to run this without the debugger first. It's coming back from the async method, and then after 8 seconds, it will come back to validate the task that happened, and it will do that on the UI thread, and then, therefore, the application crashed. Because what happened is that we come back here, we're going to do something, it's going to run something for 8 seconds, it's going to return back to the previous method, which returns the control back to the UI. After 8 seconds has passed, we throw an exception. That exception is put on this task. which is then validated back on the UI thread. The way that we fix this is by simply wrapping this, or fix this, we capture the exception. We can wrap this in a try-catch. If I run this with a debugger, click Run here. After 8 seconds, this should now tell us that there was an exception because I have the debugger attached, so it will show us where this exception was occurred. It should have. But here we can see that we threw a new exception, and I can properly handle this, and the UI works as expected. So there's quite a few things to take away from this. We should always use await with a task. We should always use try-catch to ensure that we handle those potential exceptions. Keep in mind that in relation to how this worked with the configure await or continue with, this will throw back the exceptions, right? So we have to capture them. We have to handle them. Now, another thing that I get asked quite often is, are we limited to simply using one await per method? And no, you're not. So if we'd like to run some more operations after this, we could say await task.delay. We could add more code in here. We can have as many awaits as possible. What happens here is that each time we run this, it will return back to the caller for it to execute it. Or actually, the first one will return back to the caller and then execute this work, still have that capture thread available, and come back to run that code again. Now, this is not the most efficient way possible to do this, because we might want to schedule all of these to happen at the same time. All right, so we added the async and await keywords. And this is how we validate that the tasks completed successfully. We can capture those exceptions that are potentially thrown by those tasks. If we cancel tasks, they will throw back cancellation exceptions. We should monitor that as well. Now, I also want to say we should always use async and await together. There's no reason not to. So that brings us to the implication of adding the async keyword and what actually happens internally. Because there's a lot of stuff that's going on behind the hoods here. And it's sort of using that same task approach that we saw earlier by manually appending a continue with, handling the exceptions, and capturing the dispatcher and so forth. This is all done in something called a state machine. Now, the state machine is simply something that asks us, are we there yet? Like an annoying kid in the backseat of a car. Just keeps asking us, are we there yet? Now, the implementation is actually quite clever. What it does is, so it generates this thing called a state machine that keeps track of what's going to be executed next. If it finds that there's nothing to execute right now, I'm going to come back when this work is done. It just schedules itself to run on that original thread, which is quite clever. Now, it also handles potential errors and results and sets the results on that correct thread. It runs the code after the continuation. It handles any potential errors. So all the code after await will be handled inside this state machine. So what actually happens when we introduce the async keyword? It generates a state machine, and the entire method body of that method is going to be moved into a state machine, and all of the awaits are going to be handled inside of that. If we look at a quite simple example, I'm going to take this method here. It's just very simple code where it says, I'm declaring a variable to the value 10. I have a task.delay for 2 seconds, and then a debug.writeLine. It's marked as async, returns a task, uses the await. When I compile this, that method will actually look like this. So this is just decompiled using ilspy to look at the code that's generated. It creates an instance of a generated state machine, and as you see here at the bottom, actually, what's interesting, I want to mention this as well. If we go back here, there's nothing here that returns the task, if you notice that. That is handled by this generated code. So that state machine has this task that's automatically just returned. So you can keep track of potential exceptions and results. So that is why you should mark your methods as returning tasks if you're using async. Now, if we drill into this implementation, deep into the state machine, what actually happens is that here we can see that we have our task.delay. We're declaring that variable that we used earlier or set up earlier. And what it's doing is that it's checking, am I completed or not? If it's not, then it will return out of this method. It will schedule itself to execute later. And then, after that executes again on that original thread where it scheduled itself, it runs the code inside the continuation. Like, you don't have to understand all of this or know exactly what the state machine does. Just understand that it's quite complex. It adds a lot of generated code, and that could potentially lead to errors and misunderstandings on how this works internally. This brings us to what happens if we use async void. I'm very sad if I use async void. And I see async void all the time. I just had to add it to my click event handler, and that's the only place where you're allowed to do this. For event handlers, or when there's an interface that dictates, or a contract that dictates that this is what you have to use. So is it really that bad? I guess it is, otherwise I wouldn't bring it up. Here, if I just change this to async void, instead of having async task and decompile this, no longer is it returning a task from this. No longer is the state machine returning for you a reference for you to monitor the success or the failure. So what happens if there's an exception? It's kind of catastrophic. If we go into Visual Studio, I had this quite simple code earlier, right? Where if we just undo all of that code, let's go back, or I'll just do throw, new exception, not that. There we go. And we'll just, I don't want to wait for 8 seconds. Now, I have async task, right? So what happens here is that that's going to be captured and put on the task that this state machine uses. What happens if we change this to void? This method didn't have to change at all, because the method signature is still intact. It generates a state machine that's appropriate for this method signature and our method body. Await still works. However, the code in our click handler is no longer going to be able to await that call, right? Because it's no longer returning anything. So now I'm executing this code. I can no longer use await. So it's going to run that coming back from async just immediately after it scheduled that work, right? So if I run this with the debugger attached, I'm going to click run, and do you think we're going to be able to capture the exception? No? Leading question, right? So we threw the exception. Because I have the debugger attached, it will tell us that this is unhandled. And I'll press F5, and the application crashed. Running this without the debugger attached, and after 2 seconds, the application crashes. So even though I've wrapped the entire method call, I wrapped this entire thing in a try-catch, I was unable to capture that exception. And if you understand the internals, this is kind of obvious, because what happens, if we put a breakpoint here, and actually a breakpoint down here at the bottom, I'll click run, and then quickly step through all of these lines, and now, all of a sudden, notice here at the bottom, I'm actually exiting this method. This method has completed. We no longer have that try-catch. And after 2 seconds, we got an exception, and the state machine's like, I don't know where to put this. It's probably the best to just kill your application. Like, there's a million ways they could have done this, but I guess tearing down the application is the best. So the problem here is that there's no way for me to capture this. There's no way for me to track this. And the reason that this try-catch doesn't work is because it's not executed in that context. When it comes back after 2 seconds and throws this exception, it will be thrown on somewhere else other than inside the state or the context of that method. Hence, there's no try-catch. So yes, it's really bad to throw an exception inside try-catch or inside an async void method. There's a very simple solution to this. Don't write code that throws exceptions. Or mark all your methods that are async with a task. Ensure that you validate it properly. And then you'll be able to capture that again. But of course, this requires a little bit extra refactoring. It requires a little bit extra thought into building this application. When it comes to your click event handlers and your delegates that require them to be void, you can't do anything. You have to mark them as async void Just add a try-catch and do as little work as possible that could potentially throw an exception. And you should, for most of the time, be fine. So the very simple fix is to just change void to async, and that should really just work. Now, to be efficient when it comes to asynchronous programming is also to avoid deadlocks. And we want to be sure that our applications doesn't lock up. Now, being performant and being able to distribute work and listen for that to be completed is great, but we also have to ensure that we don't run into applications hanging. Here's an example that's not super trivial to understand, but we'll get to why this is a problem in just a moment. So I schedule some work to delay for 1 millisecond. After that is done, I'm going to continue with something. The dispatcher is going to try and run work on the UI thread, but notice this thing here at the bottom. I'm blocking the UI thread. So the wait method, or the wait method you can execute on a task, will block the current context until all of this is done, but that can only be done when it can communicate back to the UI, hence we have deadlock. Now, this looks very complex. I mean, who writes code like this? What I do see often is code that looks like this. So why is this going to deadlock? Well, if we go back to Visual Studio and think about that for a second, how come this here deadlocks while adding the await does not? So this won't deadlock, but blocking the UI using the wait here will actually deadlock. Now that we know that the state machine executes code and moves that into its own implementation, we should also talk about where the state machine is executed. We're going to do something, right? So we're going to call this method. This method is going to start executing code. We're on the UI. We schedule work somewhere. Then we're going to come back, and what's happening inside the state machine is that, hey, I'd like to run this code on the UI. That would be great. However, we're actually blocking the UI here. So we're blocking the UI, therefore the state machine cannot execute its code, and therefore wait here will never complete because it's waiting for that state machine to complete, and therefore we have a deadlock. So with that being said, never block any asynchronous operations. However, sometimes you'd like to call .result, for example, on something that returns a value. So let me show you what that would look like. Let's say that we have a task.run. Let's just say that this here runs for, let's say this runs for 2 seconds. And after that is done, I'm going to return some value. Now, I'd like to get that value out of this. And the way that we do this is to use await as well. So now I have an asynchronous operation that is really just an async task of a string. And for me to get that, there are two options. Either I say, hey, I'd like to get the result from this task. This is also the same as blocking this until we have a result available, also deadlocking. Not a great idea. To get the result, we should await, and this will then unwrap that result and put it inside that result variable that we have here. So this will actually be a string. And after we've awaited that and we are sure that it's completed properly, only then can we go ahead and say, I'd like to get the result again. Now the result property will not deadlock. So you're allowed to use .result only when you can guarantee that the task completed properly, which can sometimes be tricky. So try to avoid calling result or wait. All right. So avoiding deadlocks can be quite easy. We should just avoid wait and result. We should not confuse the methods wait all with the method when all. There's a way for you to say, I have all these tasks. I'd like to wait until they're all completed. But you should use when all instead of wait all, which is kind of very simple to make that mistake. And don't share locks. If you ever have to lock an object, even with the new locking mechanism in .NET 9, there's no guarantee that you won't run into any deadlocks. And if you're sharing locks or have nested locks, it's almost a guarantee that you run into a deadlock. Now, in terms of performance and being efficient, I'd also like to talk about the unnecessary amount of state machines that could potentially be introduced. In this quite simple sample, I have a code sample in Visual Studio again. I'll show you this here. So let's take a look at this here. I have a static main method that runs a method called runAsync and awaits that. I have a method called runAsync, which awaits an internal one that then appends a continuation. It's just a long chain of methods with awaits inside of them. Like, this is not really uncommon, and I see this quite often, especially when you're layering your applications and building libraries and so forth and passing around your calls. However, each method marked as async introduces its own state machine. So if I were to decompile this, this is the same code decompiled. It actually introduced 1, 2, 3, 4, 5 state machines. And all of these different methods then have to interact with the state machine. They all have to capture the context and do all of that heavy lifting for you. Like, I'm not saying that this is necessarily badly performant, but doing this heavily in an application that is really built to be performant is not always the best idea. And this is also a good way to understand exactly how this works under the hoods. So there's two things I want to show you here. I have two tasks that are executed, but I'd like to improve this a little bit here. Instead of running these one by one, I'd like to run them at the same time and say, await both of them, and when both of them are done, you can return. So what I am going to do is to say task.whenAll, task.delay. What now happens is that we start these at the same time, and I have one task that represents the work for both of them. However, I'd still like to get rid of the state machine because I'm not really doing anything after that continuation. And if I'm not doing anything after the continuation, I can get rid of the async keyword and return the task instead. This works for the most part. It doesn't work with NV Framework or an HTTP client, but it works in situations like this here. The contract is the same, right? I return a task that someone else can await. There's nothing inside this continuation either, so how about we return that? How about we do the same here? I can probably do the same here because I'm not doing anything inside the continuation as well. So now, if I rebuild this application and inspect that decompiled code, let's see if it actually worked. Now, there's only one state machine generated, and that's for the main method of that application. A small little improvement, but for a mobile phone where you have like building a mobile app, everything drains battery, right? So try to be a little bit cautious of what you introduce. If you don't need async and await, if you don't do anything in the continuation, there's all these micro optimizations. And there's always someone that's going to tell me that, hey, that breaks the stack trace, but you'll figure that out when you get to it. All right, so if there's no need to do anything inside the continuation, there's no need to use the await keyword. However, there's this thing called async all the way. We should always do async all the way, and people keep thinking that this means that we should use async and await in all the methods in the entire chain. It means that you should await at the top level. We can still avoid introducing unnecessary async methods and ensure that we await this in the UI layer, for example. All right. Now, let's talk a little bit about canceling operations. So if I have something called a cancellation token source, I can signal to a task that you should not run. I can pass a cancellation token into a task.run. That means that this task will not start if that's marked as canceled. It doesn't mean that the method long-running operation will automatically cancel when you cancel the token. We can call cts.cancel to try and cancel this, and this long-running operation method looks like this. Now, where would that task cancel this? what would you expect happening if we try to cancel an operation that runs this code? So if I try to cancel on a cancellation token source, nothing is going to happen. That is because the code that I have here has no clue whatsoever where to cancel. We have to manually monitor a cancellation token that's passed into a method to say, if there's a cancellation requested, I can gracefully handle that. All right? Now, I do want to say one thing as well. Throwing exceptions like this here, we could also check if a cancellation is requested and exit properly. Throwing exceptions is not the best for control flow. Only do this if this is actually exception that shouldn't occur. Now, when it comes to asynchronous database operations, it's really important that we always await all the calls to the DB context, because there's no support for parallel operations on a DB context with Entity Framework. Maybe this will change in the future, but it doesn't work like that. So don't do what I said earlier about reducing the amount of state machines when it comes to EF core. Now, another interesting concept when it comes to asynchronous programming and being more efficient in the ways that we consume APIs is to use what's called streams. Streaming data is an interesting concept. Think of this like I can subscribe to data coming into my application. Very much like an event could occur. I can get some notifications as to when that data is available. You can be either the producer of a stream or the consumer of that stream. And writing this code is quite simple. So I'm going to introduce this method here, and it has what's known as an async enumerable. This indicates what type of data will be streamed from this method. So this method will, in fact, produce strings. And once that string is available, it will pass it off to whoever's subscribing to that stream. So how do I then subscribe to a stream of data? Quite simply, I use the for each. But notice where I put the await keyword. So if we jump over to Visual Studio, and let's see here. Come on, here we go. I have a Windows application. It could have been a console application or ASP.NET Core. I think it's worth reiterating that. I'm just going to get rid of this compiler error here. Async and await and tasks and all of that works in all the different types of applications. The only difference is that there's no UI in ASP.NET Core. You don't have that same dispatcher and way to cross-communicate with the threads. So here we have a producer and a consumer of a stream. So if you first look at producing a stream of data, we have a method that's marked as async, but it's no longer returning a task. Rather, it's now using an async enumerable. That means that whoever listens for this method or uses this can get a stream of strings. We can also use the cancellation token if we'd like to do that as well. Now, what this is doing is that it's using a stream to read some text from my disk. I have a while loop that's going to use an asynchronous call to read a line from that file as soon or as long as that's an instance of a string. So I'm using pattern matching to ensure that this is actually an instance of a string. It's going to continue. I know that read line returns a null string when it's actually no longer has any lines available. All right, so inside the while loop, because it's so fast reading from my disk, I'm going to add a fake task.delay to say it's taking a little time to process this. And then this is how I notify the consumer of this stream that there's a new element available, right? So I'm going to yield return. That will notify the consumer that's using an asynchronous operation to monitor this, that there's now a new line available or a new string available. So how do we consume this? Well, we have await in front of a for each loop. Normally, you see the await keyword in front of the method call. That means that I'd like to wait for this entire process to complete and then give me the data available. While having the await in front of for each means that each element from this stream of data will be retrieved asynchronously. So it will be one method call or one iteration for each element that's available. So what happens is that it's going to get an element, run this body, and then go ahead and fetch the next one. Right? So it won't buffer and read all of it. So if we look at the producer again, once you do yield return, the for each loop has to continue processing before it starts reading the next line. Okay? And then we can also pass a cancellation token into the method, and you don't have to pass it into the actual method call. So there's some interesting ways to handle that. So if I run this, it should ideally work and look okay. Let's do this. We click run here, and that's going to print my favorite song. No one knows the song, no. I'm not going to sing, I'm not going to dance, but you all know it. All right. So what's interesting here is that I've now produced a stream to a file on my disk. This could have been reading messages off a Azure message bus, for example. I could say, hey, I'd like to await for each message that's added to the queue or the message bus, and once someone adds the message, it's going to run this for each loop. So it's a really great way to consuming sources that populate data asynchronously. And finally, I'd like to talk a little bit about configure await. How many of you have heard that append configure await all over the place? Yeah, a couple? That used to be the case. You used to have to say, hey, I'd like to configure the awaiter with false, which means that once the await keyword completes, you don't have to go back to that original context. In a WPF application, that means all the code after await doesn't have to execute on the UI thread. Execute it immediately on that inline thread, take an available thread pool thread, execute it somewhere else, I don't care. This was great for libraries where you don't have to communicate with the UI. It was good for ASP.NET Core because waiting for that original thread to be available could take a little bit of time. However, I do want to say that in the latest versions of ASP.NET Core, there's no longer a synchronization context equivalent to the dispatcher. So it doesn't matter where your continuation executes. And therefore, it's redundant adding this because your process can continue anywhere. Because they no longer capture that synchronization context, there's no extra overhead removing this call. However, if you're building libraries to support older versions, or you have a problem that this solves, then by all means, go ahead and continue to use it. But think of the potential problems that you could run into. Having configure await false, if I add that by mistake somewhere inside my WPF application, thinking that this will make it more performant, because I don't want to wait for this to be able to marshal back to that UI thread. Then what happens here is the debug.txt, which updates the UI, will be unable to update the UI. We'll have an exception swallowed in this task, and then again, we'll run into the same problems that we had earlier. So with that being said, you no longer have to do configure await false, unless you're supporting older versions or building libraries that could potentially be used by older versions as well. If you want to learn more, I have a course on Pluralsight where I go through all of this in about 5 hours. We've talked about all of the important stuff in an hour. I hope you all have a really good headache, because this is quite complex. We've scratched the surface. Internally, there's a lot of stuff happening, and it's important to understand how the tasks work, how the continuation works, how the state machine works, how exceptions flow, and all of that to do this effectively. And I also want to say that in the upcoming versions of .NET, I really hope that they'll make the green threads, or whatever they're going to call it, when they introduce Async 2, which is hopefully going to get a better name, but that will add the concept of async and await inside the runtime, meaning that it doesn't have to introduce the concept of a state machine. It doesn't have to manually do all this context switching. It will just be handled by the runtime. And hopefully, that will be a lot more performant. So with that being said, I have even more courses on other stuff as well on Pluralsight, where I go through language features, how to build an operating system, a lot of interesting stuff. So I hope you enjoyed this, and if you do have any questions, feel free to send me an email afterwards. There's a little box out here. Put a green tick in the box If you didn't like it, skip the line and go to the hotel for the party. And I'll see you there. My name is Filip Ekberg. Thank you so much for coming.